All right, hello everyone. Good morning, good afternoon, or good evening, and thank you so much for joining us today. So, the topic of our webinar for today is how to integrate load, strength, and fatigue analysis in simulation for machinery. So, as I mentioned in the chat, my name is Caroline Maître, and I will be your webinar host coming to you live from Bordeaux, France. If you don't mind, you can take also a few seconds to say hello and let us know where you are joining us from today. As you may know, Siemens is a very global company, so we have people joining from all over the world. So let's see which cities and countries we have with us today. In the meantime, let me introduce our speaker and expert, Dr. Michael Hack, Business Product Line Manager for Durability Solutions from Siemens Digital Industries Software. Hello and welcome. Thank you for joining us. Well, while we are waiting a few more people to join, let me introduce a little bit the console you have in front of you. So you will see at the bottom of your browser in the center, see some icons in a widget dock. These are interactive tools you will use throughout the webinar. Just so you know, you can minimize, maximize, and scale each widget to customize your viewing experience. So I mentioned the chat window where you can interact with us and with the other participants. You have also a dedicated window for your questions. If you would like to ask questions to our presenter today, you can use the Q&A window. You can also forward this webinar to your colleagues. You can use the button at the right side using your social accounts. You can forward that to your colleagues. You can interact live with us with the emojis. Just let us know how we did today. You have also related content available to you, very important one. So don't hesitate to take a few minutes during or after the to check all these additional resources for you. So you can play and see what is more convenient with the window. So I will let you look at that. Well, right, just before we start, a short corporate speech. So welcome to Siemens Digital Industries Software. Siemens helps organizations of all sizes digitally transform using software, hardware, and services from the Siemens Accelerator business platform. Siemens software and the comprehensive digital twin enable companies to optimize their design, engineering, and manufacturing processes to turn today's ideas into the sustainable products of the future. So from chips to entire systems, from product to process, across all industries. Right, let me check the chat. We have Piet from the Netherlands. Hello, welcome everyone. Just before we start, also before I give the floor to Michael, let me ask you a very quick question. So just as information for us, to gather feedback and to learn more about you, let us know what drew you to this webinar. To learn about the solution for the first time, to learn more and evaluate if this solution will work for your team, or to learn how to use this solution more effectively. Perfect. So you can select the right answer and hit the submit button. I will give you a few more seconds and then after for today. All right. And we have also Semi from the Netherlands. Hello, welcome. Welcome everyone and thank you for joining us. Perfect. Few more seconds. I will let you select the right answer, hit the submit button, and we will be ready to start. All right, Michael, I will show you the results we have today. Okay, it's a good mix. Perfect. Nice. All right, very good. The floor is yours. You can now start your presentation. Thank you so much.
Thank you, Caroline, for the introduction, and also thank you for everybody joining us today on this web, which is, as the title also says, on integration on one side, but also on how to enable the strength and fatigue analysis in your applications. We will go into, let's say, mostly in two main topics today. The first part, we really want to see integrate a strength or a fatigue analysis in the process of design and stress analysis that you may also do already today, how to integrate that and how to make this an efficient process. So that's more or less the first part. And there, as Colin already mentioned, we also ask real users, not just presenting you some nice slides where we think why we are the best and the greatest and the nicest and the most user-friendly tools. No, we just ask one of our users to show how she is using the tool and how the tools are helping in their process and how it changed all this. And I think that's one of the most valuable things to see, not us telling you how to use it, but really see how other users are doing this. And this is maybe the first part we want to talk about, but then going up on the floor to see what happens in, let's say, for a more detailed fatigue analysis, there always is the question on where do I get my loads from? And the second part of our seminar today will go into that. We'll show you how we have new methodologies, how to integrate the acquisition of loads and definition of what loads are acting on your machine, on your machinery, how we can also improve that for the future. With that, I just start. If there are any questions, you can also put them in the Q&A session. We will go through the questions maybe at the end of the first part or at the end also of the session. Okay, with that, just go why we are doing that. Here we just have this big statement of course, we want to use simulation to accelerate the time of development, which means also the time until your bosses get the revenue out of it and maybe also your stakeholders get the money. But what does it mean for us? And therefore the question that we want to ask is really, how can we include typical test-based analysis of strength and durability requirements also early in the design process, also not only once you have done all load data analysis and a lot of things before, really when I do my design, how I already can take advantage of simulation and ensure that my requirements are also fulfilled when I do the design of my analysis, of my new parts. That's the question we want to look at. And of course, first the question is, what's the problem about that? And for that, we just had a look at what is a typical process. So of course, you design your structure, typically a CAD structure. And then of course, already today, there are a lot of tools which help you to integrate between the CAD drawings and then get to finite element analysis on the CAE side. So that's also often quite also integrated. But then once you have done this analysis or finite element analysis, you get a nice plot. You get a plot of the stresses that the structure will see when you apply the one given load or several given load scenarios that you find in some kind of requirements for the structure. But what does this really mean? And for that, it's quite often, and this is not just what I just invented, but really you're talking to people again, is, you look at data which says, okay, for this type of steel, the maximum stress it can endure is, say, 465 megapascal. And then you have to go and compare that to this colored picture. But then if you go to more detailed analysis, it even means, also be some influence of mean stress correction on the load cycle. And you have another, let's say, database or let's say lookup table or Excel sheet where you find the correction value. And then it's maybe also not just simply one plot, but you have to the load of a tension and half the load of a shear and put this together. And you all have to do that after you have done this finite element analysis and having just this whole setup of stress plots. And though we see in many situations a kind of process like that, you read really data using the post-processor, you read your parameters from your post-its or from your collections from your internal database. You enter all that into a tool, and to be also honest, quite often these tools just, let's say, some macros on some spreadsheet programs. And then you take all these results and you have to type some kind of report and give it to your manager. And if your manager has to give this to his manager, nobody really understands anymore what happens. And just to see how to improve that process, again, let's really ask our people. Let's really ask now Eva. Eva will also introduce herself, and we will see what she has to say.
Good afternoon to all of you. Today we'll talk about Simcenter 3D durability, and then specifically about how it brings benefits to our fatigue assessment way of working at ASML. My name is Eva Eggels, and I'm a mechanical analyst at ASML. So let me explain a bit about ASML and then what you do there as a mechanical analyst. So ASML is one of the world's leading manufacturers of chip making equipment. You can see one of our systems in the figure on the right. It's a common misconception that we make chips. We actually design and manufacture the lithography machines that are an essential component in chip manufacturing. So our customers are companies such as Intel who use our machines. They use our machines to create microchips that are eventually used in many electronic devices, including smartphones, laptops, and much more. ASML needs verified and safe designs. To reduce real testing cost, all designs can be virtually tested, or in other words, all designs can be simulated to already, before doing some real tests, have a feeling of the performance and whether the system meets the requirements. So as a mechanical analyst, I developed the FEM models in order to do so, and also perform the analysis in order to do so, to support and drive the design of these systems. Then a bit about the organization. ASML has more than 100 technical competences on various topics, such as safety, bolts, vacuum, and more. Really the core of ASML's technical knowledge sharing, and really at the core to enable the technologies needed for our systems. I am part of the technical competence, mechanical and competence. All my colleagues within this competence are able to do mechanical and thermal analysis, and by that supporting projects across the company for a longer or shorter period of time. And these projects can vary a lot. It can be within the development and engineering department, but also in the research department. By doing these analyses, again, we support and drive the design of these lithography systems. Well, what is my link with fatigue assessment and why is it relevant for ASML? Our competence, mechanical and thermal FEM, consists of several focal areas. When talking about a focal area, you can think of dynamics, thermal optimization. And as analysts, you can join one or more of those focal areas and really contribute to the way of working within that focal area. So you really contribute to the guidelines or the way of working. Everyone should then follow the set guidelines to ensure the quality of our work. New insights or new needs ask for updates to the way of working. So yeah, it's under constant development. And I myself am contributing to the way of working for fatigue assessment. Then a bit about why fatigue assessment is relevant for ASML. Well, we want to prevent fatigue failure, or at least guarantee a certain lifetime for our parts and modules. One example is shown in the animation on this slide. You can see the wafer stage. It's a key module in our lithography systems. So in the animation, you see the wafer stage. On the one hand, on the one side, it's measuring a wafer, and on the other side, it's exposing a wafer. And as you can see, it happens at high speed, involving high accelerations. And this module should then be able to withstand these high accelerations for a long time, for a large number of cycles. And that's where the topic of fatigue comes into play. And this is just one example, but yeah, given the complexity of our systems and the high speeds on which it all operates, of course, there are more parts of the system where fatigue becomes really relevant. So let me talk you through how durability can positively impact fatigue assessment at ASML. In order to show the benefits, let me first explain how fatigue assessment takes place in cases without using durability. So let's first take a look at a simple example. You can here see a beam. So typically as a first step, you do some FEM modeling, FEM assessment to determine the stresses in a part over time. In our way of working, there is an Excel sheet which is then used to perform the fatigue assessment. So you enter some data in this Excel sheet, material data, stress data from your FEM modeling, and then this fatigue Excel sheet can tell you whether you're okay in terms of fatigue assessment or not. And it includes some of the typical fatigue assessment aspects, such as mean stress correction, safety factors. And this approach can be followed for simple cases, but of course also for a bit of a more complex one. Over here you can already see the geometry of the part is a bit more complex. We might have more stress concentrations. Additional complexity also comes in from multiple load cases or longer time histories. And in those cases where it gets more complex, you cannot avoid some bookkeeping. So typically you add in another tool or another overview to really keep track of the analysis you've done, the fatigue assessment outcomes, and to just see where you are in terms of your fatigue assessment. And so for both the simple and the complex case, Simcenter 3D durability can really help. I investigated the use of Simcenter 3D durability myself for a case study. One of the first questions we had is, can this Excel sheet, as we had in place before, to do the fatigue assessment, the functionalities that are included there, can we also use or follow or integrate those functionalities within durability? In other words, do we still need that Excel sheet? Or can we, by smartly setting up the analysis and durability, also do the assessment there? And it turns out that it's possible to follow the exact fatigue assessment way of working from the Excel sheet also in durability. So the Excel sheet is not needed anymore. I updated the logo now with Simcenter 3D durability. And also what really helps is, since you can directly perform fatigue assessment on your FEM results, you need less bookkeeping and an external tool, but you can also again immediately keep the overview of your assessment within Simcenter 3D durability, and that's also a big advantage. So even though you might use another FE package in order to get the stresses, all the rest, the fatigue assessment and the bookkeeping, you can do that in Simcenter 3D durability. So it just avoids that additional step from going from a FEM package to an Excel sheet. Thereby it reduces effort, risk of errors, and that's really nice. Well, in this slide, we will further zoom into the advantages, of which I already briefly touched upon a few of them in the previous slide. So as mentioned, fatigue assessment can be performed directly on your stress data coming from FEM. So you don't need to transfer your FEM data manually to an additional tool. You can directly see the critical regions within your model. It's not just a cell in an Excel sheet that gives you a certain value and then you need to again make a note of where that value occurred. No, you can really, for example, with colors, highlight these are the regions that are critical in terms of fatigue. Another advantage is about the stress definition that you use. Typically we use principal stresses for that. That's a bit more complex than equivalent stresses, such as for mices, because it's not just a single value, it's not a scalar, but it's 3 values with a certain orientation. And when dealing with this manually, you need to be careful. It's prone to errors, and durability can automatically deal with these stresses for you, which saves time, reduces risk of error. Also, you can efficiently analyze long time histories or many load. It avoids the need of manually selecting some critical load cases, which costs time and can lead to either be too conservative, assuming all kinds of worst case cases, but on the other hand, also by being able to compute all of them, you are sure that you don't overlook a critical load case. So that's also a big advantage. Now finally, compared to this Excel sheet that we used before, durability has a lot more opportunities for additional analysis. For example, I showed here a bar chart, and that tells me for one of my analysis which loads really contribute to the high alternating stresses in my structure. And that can then also serve as a guidance for design improvement. So if you know which loads contribute to the stresses in the critical locations, then that might also give some guidance on how to improve your design if the stresses are too high, if your fatigue assessment is not okay. So the tool durability will help us in identifying where, when, and why fatigue failure occurs. It can help in preventing errors, and it makes the overall workflow more efficient. So that brings me to the end of my slides, and I hope I have been able to give you some insights in why fatigue assessment is relevant for ASML and how we get the best out of durability, where we really see the benefits of durability compared to our previous way of working. Thank you for your attention.
So big thank you to Eva for this very nice, but also very insight in her processes. Unfortunately, as you may have also seen, she cannot join us live today, but she had this pre-recorded slides sent to us also for this presentation. I think I hope I learned a lot of it, but I also hope that you learned quite a lot of it on what is really the main topics of where you can really get more efficiently your results, but also I think avoiding bookkeeping in some other tools or somewhere else, it avoids a lot of potential errors. And this I think you should keep in mind from this presentation of Eva. Okay, summing up a little bit of what she already has presented, I'd give you a little bit of background here also on how we did that, not only that we did it, but also how we did it. And one thing we integrated there is what we call the strength and durability wizard, which means the wizard automatically takes up the finite element analysis. It looks up into and sees the kind of analysis it is. Is it a nonlinear analysis, a linear analysis? And it automatically provides you more or less the best idea of how we do fatigue analysis. And it also helps you to select the material data, but it also can create fatigue material data on the fly. And so that's one important point, that you don't have always to run to the expert or to have a big book on how to do this step by step. You always do it in the same way, and you have a safe setup for doing it, not only for getting the stress results, but really instead of getting the stress plots, you get such a traffic light type of plots, which tells you exactly in that what it means with respect to the loads and already including all the properties of the material. So instead of looking up what does 355 megapascal mean for this material, you directly get here set by the tool, you are 20% above the load limit. You have to change still your design. Typically, you won't get that. We just faked a little bit these plots to get it a little more colorful. But the main point is you directly get a plot which is completely green and you can go on, or there's some yellow parts where you have to think about is this good enough or not. It's not, there's no more interpretation. We directly do all the analysis and you directly get the results that's needed. That's not much, let's say from a pure method point of view to get a strength plot, but there's such a big difference between just the stress plots and the plot which gives you really the answer to the question, am I in my design guidelines, and how far, if not, how far I'm away from it. And it is giving you much more information also directly without, let's say, doing a lot of analysis, but directly get it by the wizard. So that's one important step that leads to all these answers or all these process improvements that Eva mentioned before. So that's more or less on the design side, on the design analysis side. But now, next step is, of course, there are also fatigue experts in the company, like in ASML. And how can these guys then also work together if on one side there's a simple tool for strength and with the wizard, and on the other side there's a high-end fatigue tool. And that's maybe also something you have seen in your life, that these simple tools and these completely independent from each other, and so they don't talk to each other. And that was also one of the main points that we took into account when developing this wizard part. We had been just putting in there also a very important step to say, okay, you can already start by defining your analysis, for example, even just a strength analysis using the wizard. But then the expert can take up exactly the same analysis, just copy it, and then add fatigue data, add load data, add some special fatigue parameters, but still working on the same FE model, and you are sure you are working on the same FE model, and maybe also if you are using the same loads, you also have the same load data. So you always work on the same thing, and you don't have to be careful that you load up some kind of finite element result from somewhere. Everything is still in the same environment. Also seems simple, but again is a lot of, let's say, helping you keeping away this bookkeeping. And this, I think, if somebody else is doing the bookkeeping for you, you have time to improve your work and you have time to improve your structures instead of doing stupid stuff which has no real added value but needs to be done. So that's the first point. Really also integrate the work of the strength analyst and the work of the fatigue analyst. Of course, for the fatigue analyst, everything is there that is needed, but you know you work on the same model, you know you work on the same setup. Next step, do we really also get all the answers to improve the design? Also there, Eva had already mentioned that. I just put in here a little bit the global process that we typically, let's say, would promote to do there. There may be different load events in your analysis. So meaning maybe some heat up phase, there's some steady state phase, there's some cool down phase, or there are other parts in depending on what kind of, let's say, machinery you are using there. And in the first step, you directly see which of those events are the most important ones with respect to the highest stresses, with respect to the lowest safety factors, but also with respect to lifetime. You get just the color, you get just the bar chart, and in this case, you see the third one. This is the important one, and then you focus on this third event. Then you do a more detailed analysis directly on your finite element mesh, where you can get all kind of results, all kind of durability results, all kind of stress results. You can see what is the maximum stress occurring there, what is the maximum stress amplitude. You can see what is the safety factor with respect to fatigue, safety factor with respect to static results. Everything you can then see there directly on the complete mesh. And if you then identify there are some regions where a lot of things happen, you can do a local analysis and see, for example, when in the, let's say, load history, some damages occur. Or what Eva mentioned before, which of the loads which are applied there on the structure have the highest impact on the fatigue life. All this then is done in the third step. And here now you can analyze the why and the when, and before what load event is important. So for each of these different questions, we also add special tools in there, and of course this is also then helpful for the expert. For the design analyst, we have the direct feedback, getting the traffic light type plots, red, green, yellow. And here for the expert, you can really do any type of detailed analysis, giving you really then the answers on why there is a fatigue problem and what you have to do either with respect to the load flow or with respect to the design of the structure. And then you can go back, redesign, let the design analyst rerun his strength analysis, and you come back to the fatigue expert, and everything is set up again. So you don't need to redo anything or reassign some fatigue parameters. Once you have done it, you can change everything and you can get the new results. That's the important point of the global workflow. I hope that's really the main point of integrating fatigue directly into tools which do also the finite element analysis. Okay, so that's really more or less on the main workflow part. Getting a little bit into is this really some cheat codes which can be used because this is just now coming from Siemens? No, it's not coming from Siemens. It's really a 30-year long development that we do here in our team where there still are people in there from this stage for 25 or 30 years who have developed a lot of the new stuff on methods in fatigue and really worked on that for many, many, many years. So it's not just something bought somewhere and put into a big, let's say, tool. It's really based on 30 years of fatigue analysis. Coming then, of course, having all this big slide with all these many methods on there, there's always a question, is there a best fatigue analysis methods? And once you ask it, you go to people, this is a question you get very, very often. But answer is, it depends. It's like, it depends on the application, but it also, not only on the application, it also depends on the data which is available, but also on the experience of the user. If you have done some kind of method for many, many years, you're feeling much better, have much better feeling than for another method. And you cannot just say this method is better or less good. It's really something which depends. And therefore, we have included into our intelligence to see what kind of data is available and taking up what kind of data and what kind of parameters the user gives, it chooses the methods to choose. So just a simple example is if you know something about the mean stress dependency of your material, you add that, and then the solver uses mean stress correction. If you don't know anything and you say, okay, I don't know it, then you leave it off, and then the solver automatically chooses a method without mean stress correction. So that's a little bit of the intelligence of the solver, but to make this also working, we have also done, let's say, a kind of a template concept. And I think that's important enough to give you a little insight into that. The idea is you have also in your companies the experts teams, like we have seen Eva, and she creates these analyses for different types of applications, and the end users are just selecting them depending on the application. What does it mean? So what does a template look like? So first, we have some typical type of fatigue methods, like stress life or strain life or these kind of methods. And for each of those, we have a predefined open template, which typically defines a set of parameters. Once you say, okay, these parameters that are just given by those, I want to use for my application, but I want to use exactly those. For example, I have a special mean stress correction method. This is Walker, which is typically used in aero industries quite often, or any of the other methods used here. So you define these setup, meaning a combination of the stress life methods with all these parameters which fill into the method. So that's the first step you do, you define that. And then the next step is just to say, okay, I create now a new analysis template from that. It's just a button click. And once I do that, I can now decide if those parameters that I have set should be still available for the end user to change, or I want to fix it. And you can just take them up here from the list of parameters which may be changed to this small part down here, which is called implicit parameters. And though you just have a reduced list of parameters, for example, here in this case, you will call it you use it for casted structures, and you give it a name, casted structures and stress life. You use these parameters. You just put it into your company database, again by one mouse click, and then using it, the end user just sees when he chooses this template a very restricted number of parameters. And this really makes the whole process much more robust to be sure that using this kind of templates, the end user will always be on the safe side. Okay. And that's just again what we had in mind for that. So this just the idea of what is simple. And simple is not just making everything off, but meaning simplicity is really some kind of the best compromise between too little and too much. And we tried really to work on that. And in principle, I just wanted to mention we had that in mind when creating all our methodologies. Okay, so then how do I get realistic loads? That's now the second part, and I hope first part had been clear enough to see how did we do this integration of finite elements, durability tool or strength and durability tool together with the intelligent post-processing to make life as simple as possible. The second part now, and we have to get a little bit faster now, is how to get realistic loads. And that's typically also one of the main problems that I have. In many cases, those load scenarios are just defined in handbooks, recommendations, regulations. And then in this part, if you have that, the efficient integration, of course, is useful. But we also support anything from simple linear load steps through superposition to full nonlinear analysis. But you also, in some cases, those load scenarios are time or frequency based. And all that can be combined, and it's important that you then can see what is the influence of the different parts of your load scenario. Just a few examples here. You see here, in this case, you have a nonlinear analysis of this body. You do a strength analysis of the load up, and you do a fatigue analysis then on the cycle of when there's pressure inside and outside. So here you just get the strength analysis of the bolting, and then in the end you get, of course, some pre-stresses here, and this leads to fatigue influences once you cycle the inner pressure in here. So that's a typical example. More complex things are if what Eva also mentioned before, you have complex, let's say, load waves, as you've seen before, some forces acting on your structure. And in many cases, they are much more than these 10 different load cases you have on this simple body here. So they are often something like 100 degrees of freedom. And if you want to control that, you just put in quite a lot of effort in making that easy. But it is also realistic if it comes from also just from these books and recommendations. In other industries like automotive, people did a lot of effort in getting really then to the realistic loads. So they do a full digital twin simulation. But also for that, of course, they did just not say, I take the effort to do that. You still need to know a lot of things, like you have an automotive application, you need to know what is really the road I'm driving on. You need to know how the driver is acting, so you need a driver model, and you need to know all the maneuvers. And this is really something which in the automotive industry is running quite well, and you have all the tools to do that. But in many cases, this is not really realistic that you get out there. For example, if you have something in the agricultural industry, you are driving on soil. And soil is completely different than a road. And also let's say, the interaction between the tires and soil, completely different. And in other cases, to get to the maneuvers, that's really the problem. And for that, we went one step further, of course, to the approach on getting the loads. You can still do that with a system level approach. You model, for example, a complete reloader, and you want to know what on this boom here, what kind of local loads are on there, and you can do this with the so-called multi-body simulation. And this integration with durability. You may have seen on the slides before, that's something which is well established. We do that for, let's say, 20, 25 years now. But still, knowing the maneuvers is still an issue. And how do I get to the real maneuvers? And that's a thing where we now went to a new definition on the operational loads. How do I get the operational loads from simple measurements? And there we now have new tools which we call smart virtual sensing, which is able to do some measurements and back calculate from the measurements directly with a predictor tool or some kind of, let's say, data fusion tool, as we call it nowadays, more scientifically. So we can then back calculate the loads and always adapt it to the measurements that we have there. So that's the basic idea, and of course with that then you can also then get the result, the real loads which are acting on your structure from real measurements. And in the next step then also of course doing it online, meaning do it in operation to get in operation on such a sub model. You can get the loads acting on it and get the fatigue data directly on it. As mentioned, we use this smart virtual sensing tool. Our colleagues always call it measure the unmeasurable. So you have a few strain gauges with the tool and the correct ROM. You get the stress strain on your structure you're interested on for the full load time that you measured. So this is just one slide. I don't go into the details. It's a prediction correction method. And the great point about that is it also takes into account the uncertainty in the measurement. It's not something which tries to adapt the model, but it's in each step you also take into account the measurement errors, the potential measurement errors, and then with that, a few initial cycles, you really get very, very close to the real operation. So that's what we use there. For the experts, we use the Kalman filter approach there. And this allows you really to get to the operational loads. And with that, the next and let's say step, what you still need to do is where do I put my strain gauges for the measurement? And also for that, we integrated some tools to do this, to find the optimal sensor placement before the analysis. And so actually you have a tool which tells you which are the most important points in the structure where I can put my measurements. Of course, first step is you tell the system where you can place measurements, and then it tries to minimize really the amount of measurements which are needed. And they can be quite far away also from the load application points, and can also have some influence from different load application points at the same point. And the tool tells you which are the best places or the optimal places for the measurements. Done that, so actually here you put on a large pool of potential measurements. You do some analysis with some loads on it, and then you get some kind of optimal layout. Now you have an optimal layout, you measure them, and you go to fatigue. So that's the whole process. So we did this for this kind of example here, and to be sure that what we are doing there again is reproducible. So we did it in a kind of hybrid mode in, let's say, for this project. What we did there is we first calculated the strains that we used for the back calculation already with multi-body simulation tool, where we already knew what are the real durability results which come from the multi-body based load prediction. But we now did it using this new tool where we just calculated from multi-body, we calculated the strains at I think 16 different positions here, and then back calculated the load again and get more or less the same distribution of damage and the same damage or the same lifetime predicted by this operational loads, given by the few measurements, knowing now that if you put our measurements at those points in a real structure, we can use these measurements directly to back calculate the loads. And that's what we did on that. So you see here that the fatigue, the distribution that you get there, that they are very, very small fatigue values. So luckily you can use this structure for loading it. So what we simulated there, just to pick up, let's say, weights and then drive around. And what you see here on the left-hand side then is that these are the different additional local analysis which we do there. You see here what is that there is damage created. So in the upper picture here you see the damage, and in principle there's only damage created in this short time frame when this reloader is picking up some loads. And which also means if you do some tests, don't have to drive the thing around, nothing happens there, even without and with loads. Only, let's say, the loading situation itself is important there. And this is already some kind of output you get directly from this kind of analysis. But again, you now know where to instrument your structure in real life. You can create real life load scenarios. And also in the second step now, then what you also can do if you have the measurement devices simple enough, you can even do this in operation, which means you really know how long your structure will still live due to the real loads which are acting on the structure. So it can also be used in the future for predictive maintenance. So today we have this combination as I showed today. And next year, we also will have the full, let's say, the full in-operation, the full online calculation of remaining lifetime and also then of predictive maintenance. So that's the next step that we are doing there. Okay. With that, so that's more or less what I wanted to tell you in the second part. The integration of strength and durability in what we call the digital twins. It's very important to have it in CAD, finite element, and the durability analysis, but then also the integration of tests. This really is essential if you want to apply it, and also for knowing the robustness. So instead of just looking up, let's say, some kind of load scenarios from a book or from, let's say, from some kind of recommendation certification units, you have a much better knowledge of your real loads, and then you can ensure the real quality of your products and not such something which is more or less independent from that. And there's one thing, just maybe you may remember that some years ago, some 20 years ago in Germany, they had a big catastrophe on trains still, where this fast train, there had been this catastrophe with a fast train, and that was just a fatigue problem. And the basic problem was that they used very old, say, load scenarios, which were not adapted to fast trains. So in some cases, it's even dangerous to use this over this typical load scenarios from a book if they are not adapted to the real life usage. But in most cases, they are just overestimating your damage and you over-design your structure. Okay, and as mentioned, so the next step is the integration of the measurement and simulation with this smart virtual sensing solution that I showed you in operation. So this is something we are just in the moment in development, and that then also will allow real health monitoring during the life of the structure. You can see where you are in the life of the structure, but also allows predictive maintenance, not, of course, not too late. Predictive maintenance too late, again, that's the catastrophe of the train, but in many, many cases, it's much too early. And so to get there, let's say a better compromise between safety and Also then, let's say, efficiency, predictive maintenance will be a very important point. I think not only I think in future, but everybody I ask. And then also things like if you want to do something like hardware as a service, so you lend your machines to somebody. For that, let's say this damage accumulation during life really also helps you to give you a much better, let's say, business model for that. Okay, I think with that, we are on questions and answers, and I already see here a question. Caroline, you want to say something?
Sure. Yeah, sure. Thank you. Thank you so much. Thank you, Michael, for this great presentation. Also, thanks to Eva for recording and to this great presentation. As Michael mentioned, it's time for the Q&A session. If you have any questions for him today, do not hesitate. You can type them in the Q&A. You have also the chat window. We have 5 minutes, so just a bit less, but don't worry. If you have any other questions, you will receive feedback from our speakers offline over the coming days. I have a question from the first one. Let's see in the list. So the first one from Francisco. Maybe it will be something you can take offline, but could you share the presentation of the analysis sample, please? So maybe it's something.
Yeah. So I think
template.
That's really, I think, presentation anyway. So that's an easy one. Yes, it's in the presentation.
It is in the presentation, and also in the related content you will find the slides from presentation of today, so you can also have a look, download the presentation and have a look. And a question from Revati. So what is the difference between Simcenter 3D, Star CCM Plus and EFT, and what can be a good starting point for a small business? Good question.
That's a very good question, and also a question that we also have to ask us very often. So the one point, of course, clearly is, of course, that there are different goals of the different tools. So the Simcenter 3D tool is doing everything which is typically based on 3D, therefore 3D finite element calculations. So it starts typically by finite elements. Does acoustics, fatigue. So fatigue here is really in the Simcenter 3D parts. Thermal analysis. There are also some solvers also in there, but the main focus there is really on flow, and they have great tools for that. And flow AFD typically gets on thermal analysis based on flow. Let's say some example which heats up. And with that, you can then calculate the thermal flow in your structure. And from the thermal flow, then you get some stresses, which then you go back into Simcenter 3D. For other example, you may have an exhaust system. There's hot gas going through the exhaust system. You can use Star CCM to calculate then the temperature distribution on the exhaust system. With that, you go back to Simcenter 3D, do a thermal structural analysis, and add to that a fatigue analysis. So it's typically, there are often workflows which combine all these things, and that's also one of the reasons Caroline also mentioned at the beginning, the idea, but also the big idea of Simcenter as a global idea, where we want to combine those different applications into applications. And really, this is then something where we have to see how to combine all these differences. And the question, what is a good starting point for a small business? It's also the question, what do you want to do? If you want to do fatigue, you will. If you want to do finite elements, use the Simcenter 3D. If you do some kind of a flow analysis, you need to use Start by Star CCM Plus. But goal for us is to integrate all of that in the future to make it more easy also for small businesses to get the best starting point. All the work we do, for example, with cloud solutions and software as a service, of course, go in this direction, that you can combine for the different needs, you can combine then the solutions that you need. Okay.
Thank you so much, Michael. Yeah.
I just hear the sounds. We are finished. With that, I also thank
Yes.
everybody keeping on. And of course, you also know you can also in the future have this stuff you also download it, can hear me again, can listen to me again, to Eva. If there are any more questions, just also contact Caroline. Maybe you can also then, she will then contact me and we'll answer all the questions that you still have. With that, thank you
Exactly,
again.
exactly. Thank you
It was
again. Thank
great.
you everyone for joining. Yes. Have a great day or
And
evening.
goodbye.
Thank you.
Bye bye.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.